Welcome to this quiet journey into the deep cold waters where ice meets ocean. A gentle exploration designed for those peaceful moments when the day has ended and the night stretches out before you like a calm frozen sea. Wherever you are listening from right now, whether nestled in the comfort of your bed as darkness settles beyond your window, or perhaps sitting in a quiet room as the world outside grows still, I invite you to settle in completely and prepare for a voyage unlike any other. Tonight we will drift together through the ancient mysteries of icebergs, those silent wanderers of the ocean, exploring their hidden depths, their secret journeys, and the profound ways they shape our world in the quietest of movements. Before we begin this tranquil expedition, if you enjoy these long, peaceful journeys through Earth's wonders, please consider liking this video and subscribing to this little small channel to motivate us to create more of these calming explorations into the mysteries that surround us. Let your shoulders drop away from your ears now. Let your jaw unclench if it has been holding tension. Let your breathing slow down to match the rhythm of calm waves lapping against ancient ice. Feel the surface beneath you supporting your weight entirely so that you do not have to hold yourself up anymore, so that you can simply exist without effort in this moment. We will take our time with everything tonight, moving slowly like an iceberg drifting through polar waters, letting each concept settle into your mind gently before moving on to the next. There is no hurry in the frozen realms. Icebergs have been carving from glaciers for millions of years, and they will continue their silent journeys for ages to come. And in that vast expanse of time, this moment right now is yours to simply be at peace, to let your thoughts become as soft and diffuse as fog rolling across Arctic waters, to allow yourself to sink deeper into comfort with every breath you take. Birth of the silent giants. As we begin our slow drift into the world of icebergs, let us first appreciate how these magnificent structures come into being. For an iceberg's story begins not in the ocean, but high on land, in the vast ice sheets and glaciers that blanket the polar regions of our planet, accumulating snow year after year, century after century, compressing that snow into dense ancient ice that holds within it the frozen memory of atmospheres long past. The process of iceberg formation, called carving, is both violent and strangely beautiful, a moment of transformation when ice that has been part of a glacier for perhaps thousands of years suddenly breaks free and begins a new existence as an independent traveler of the seas. Imagine standing at the edge of a massive glacier where it meets the ocean, the ice cliff rising perhaps 200 feet above the water's surface, glowing in shades of white and blue that seem almost unnatural in their intensity. And within that wall of ice are layers upon layers of compressed snow, each layer representing a winter's accumulation. And if you could read these layers like the rings of a tree, you would find a record of climate conditions stretching back through time. Capturing the composition of ancient atmospheres, the temperatures of forgotten summers, the volcanic eruptions that dusted the world with ash, all preserved in frozen suspension, waiting to tell their stories to anyone who knows how to listen. The glacier itself is not a static thing, but a river of ice moving slowly downward and outward under its own immense weight, flowing like an incredibly slow liquid, deforming and creeping along at rates that might be measured in meters per year or even meters per day in the fastest flowing glaciers. And this movement is so gradual that it seems imperceptible, but it is constant and inexorable. Driven by gravity and by the accumulation of new snow at higher elevations, that pushes the older ice downward and outward toward the sea. As the glacier advances and reaches the ocean, its leading edge extends out over the water, forming what is called an ice shelf or a tidewater glacier front. And here the ice begins to experience new stresses, for it is no longer supported from below by solid ground, but is floating on water or is cantilevered out over the water. And the tidal movements and ocean currents create forces that the ice has never experienced before. The warming ocean water also begins to melt the ice from below, carving away at its base, creating hollows and weaknesses. And as the ice continues to flow forward from behind, these weaknesses grow into cracks and fractures that spread through the ice like slow lightning frozen in time. Eventually, the stresses become too great, and a section of the glacier breaks away, sometimes with a crack like thunder that echoes across the frozen landscape, sometimes more quietly with a deep groaning rumble that seems to come from the very heart of the ice itself. And in that moment of separation, an iceberg is born. The newly carved iceberg does not simply fall into the water with a splash, but performs a complex ballet of motion and transformation. For as it breaks free from the glacier, it is suddenly released from the forces that held it in place, and it begins to respond to new forces, gravity pulling it downward, buoyancy pushing it upward, and the shape of the iceberg and the distribution of its mass determining how it will move and rotate as it enters the water. Some icebergs carve relatively gently, sliding into the ocean with a slow majesty, creating waves that radiate outward in concentric circles, carrying the iceberg's energy away from the glacier face. Other carvings are more dramatic, with large sections of ice toppling forward like felling trees, plunging into the water and disappearing beneath the surface before bobbing back up in a fountain of spray and smaller ice fragments. The released energy creating waves that can be dangerous to nearby ships or wildlife. And the sound of these carvings, the crack of ice breaking, the roar of ice striking water, the hiss and rumble of displaced water rushing back, creates a symphony of natural sounds that speaks to the power and beauty of these transitions. Once in the water, the iceberg begins its journey of adjustment, for the piece of ice that broke from the glacier is unlikely to be in a stable orientation, and so it rocks and rolls, seeking its equilibrium, the densest parts sinking lower, the lighter parts rising higher, and this process can be dramatic, with large icebergs rotating and even flipping completely over as they find their balance. Each movement creating more waves and revealing surfaces of ice that have been hidden within the glacier for centuries or millennia. Surfaces that may be different colors, may contain different patterns of bubbles or layers or inclusions, telling the visual story of the ice's formation and history. The hidden architecture beneath. As we drift deeper into understanding these frozen wanderers, let us turn our attention to what lies beneath the surface. For the most striking feature of icebergs is that what we see above the waterline represents only a small fraction of their total mass. The famous tip of the iceberg that has become a metaphor for hidden depths in countless contexts. The exact proportion varies depending on the density of the ice and the salinity and temperature of the water, but typically about 10 to 15% of an iceberg's volume extends above the water surface, while the remaining 85 to 90% lies hidden below, an enormous mass of ice extending downward into the dark waters, often reaching depths of hundreds of feet, or even in rare cases, more than 1,000 feet. creating underwater mountains of ice that are invisible to anyone observing from above. This hidden architecture gives icebergs their unique character and behavior, for the underwater portion of an iceberg is subject to currents and temperatures and forces that are different from those affecting the visible portion, and these differential forces cause icebergs to move in ways that can seem mysterious or unpredictable, drifting in directions that do not align with surface winds, rotating slowly as different parts experience different currents. Even diving deeper or rising higher as changes in temperature and salinity affect their buoyancy. The shape of the underwater portion of an iceberg is often very different from the shape of the visible portion, carved and melted by warmer waters, by the mechanical action of waves and currents, by the presence of warmer or saltier layers of water at different depths. And this underwater sculpture creates forms of extraordinary beauty and complexity, ridges and valleys, caves and overhangs, surfaces that are sometimes smooth and polished by the water's movement, sometimes rough and pitted where melting has been uneven, sometimes colored by inclusions of sediment or algae or minerals that were captured in the ice when it formed. The underwater portions of large icebergs can extend horizontally as well as vertically, creating vast submerged platforms or shelves that can be dangerous to ships that venture too close, for these underwater extensions are invisible from the surface and can extend far from the visible portion of the iceberg, like hidden underwater claws reaching out in all directions, and many maritime disasters have been caused by ships striking these underwater portions. The collision happening in waters that appeared safe based on the visible distance to the iceberg. The most famous of these disasters is of course the sinking of the Titanic, which struck an iceberg in the North Atlantic in 1912, and the resulting loss of life and the shock to public confidence in maritime safety transformed how ships navigate through ice-filled waters, leading to the establishment of the International Ice Patrol and to new regulations about ship construction, lifeboats, radio communications, and ice monitoring. The temperature of the ice itself varies throughout the iceberg's structure, with the surface ice being closer to the temperature of the surrounding air or water, while the interior ice can be much colder, preserving temperatures from the glacier from which it carved, and this internal cold can persist for months or even years as the iceberg drifts through warmer waters. For ice is an excellent insulator, and the outer layers of melting ice actually protect the inner core from rapid warming, creating a thermal gradient that affects how the iceberg melts and changes shape over time. Within the ice are countless tiny air bubbles, trapped when the snow was compressed into ice, and these bubbles contain samples of ancient atmosphere, with the same composition of gases that existed at the time the snow fell, making icebergs and glacial ice valuable archives of climate history. And scientists who study ice cores drill into glaciers and ice sheets to extract these records. But drifting icebergs also carry this information with them, slowly releasing it as they melt. The ancient air bubbles escaping into the modern atmosphere, creating a quiet hissing or crackling sound that sailors and researchers near icebergs often notice, a sound called Berge-Seltzer, like the fizzing of a carbonated drink, as thousands of years of trapped air is released all at once. The classification of ice. Let us now drift through the different types and categories of icebergs, for not all icebergs are the same, and understanding their variations helps us appreciate the diversity of forms that frozen water can take as it journeys through the ocean. Scientists and mariners have developed classification systems to describe icebergs based on their size and shape. And while these categories are somewhat arbitrary, they provide a useful vocabulary for discussing these frozen structures. The smallest pieces of ice that carve from glaciers are not technically called icebergs, but are instead called burgibits or growlers, with burgibits being larger pieces that extend 1 to 5 meters above the water surface and have a mass between 100 and 300 tons, while growlers are even smaller, extending less than 1 meter above the surface and having a mass less than 100 tons. And both can be dangerous to ships because they are difficult to detect on radar and can be easily missed in rough seas, floating low in the water like floating mines of ice waiting to damage unwary vessels. True icebergs are larger than burgibits and are further classified by size into categories that range from small icebergs, which extend 5 to 15 meters above the water and have masses up to 200,000 tons, to very large icebergs, which extend more than 75 meters above the surface and can have masses exceeding 10 million tons, containing enough fresh water to supply a large city for months or even years. Beyond size, icebergs are also classified by their shape, and the shapes that icebergs assume are determined by the way they broke from the glacier, by how they have weathered and melted since carving, by how they have rotated and found equilibrium, and by the structure and layering of the ice itself. The most common shape is the tabular iceberg, which is characterized by a flat top and steep sides, often looking like a floating table or platform, and these icebergs typically carve from ice shelves, the flat extensions of ice sheets that float on the ocean. And because ice shelves are already floating when pieces break away, tabular icebergs often maintain their flat-topped appearance for long periods, slowly eroding from below and around the edges, but retaining their characteristic shape. Some tabular icebergs are truly enormous, with areas measured in hundreds or even thousands of square kilometers, and these giants, sometimes called ice islands when they are exceptionally large and flat, can persist for years or even decades, drifting slowly through polar waters, serving as temporary homes for seals and penguins and other wildlife, even hosting temporary research stations where scientists can work on the stable ice surface. Non-tabular icebergs come in a greater variety of shapes, classified into categories with evocative names that describe their appearance. Dome icebergs have rounded tops, created by extensive weathering and melting that has smoothed their upper surfaces. Pinnacled icebergs have one or more spires or peaks, often formed when an iceberg breaks into pieces or when differential melting creates vertical structures. Wedge icebergs have steep sides on one end and a gentle slope on the other, often formed when an iceberg has rotated. Drydock icebergs have a U-shaped slot or channel carved into them, sometimes formed by wave erosion at the waterline, sometimes created when an iceberg breaks apart in a particular way. And blocky icebergs have steep sides and flat vertical faces, often appearing angular and geometric. The shape of an iceberg is not permanent, but evolves continuously as the iceberg drifts and melts. And this evolution can transform an iceberg from one category to another, or can create hybrid forms that defy easy classification. And the most dramatic changes occur when an iceberg becomes unstable and rolls or flips, an event that can happen suddenly when melting has changed the distribution of mass enough that the previous equilibrium position is no longer stable. And when this happens, the iceberg rotates to a new orientation, often revealing surfaces that were previously underwater, and these newly exposed surfaces can be startlingly different in color and texture from the weathered surfaces that were previously visible, sometimes showing deep blues or greens, sometimes showing layers or patterns that were formed in the glacier, sometimes revealing inclusions of rock or sediment that were carried along in the ice. The rolling of icebergs is a hazardous event for anyone nearby, as the movement displaces large volumes of water and creates powerful waves, and the rotation itself can take minutes or even hours for very large icebergs, a slow-motion transformation that is both beautiful and terrifying to witness, as thousands or millions of tons of ice slowly revolve, creaking and groaning, water cascading from surfaces that rise from the depths. The iceberg seeking its new equilibrium in a dance dictated by physics and buoyancy, currents and the journey of ice. As we continue our gentle drift through the mysteries of icebergs, let us now explore how these frozen giants move through the ocean, for their journeys are determined by forces both visible and hidden, by surface winds and deep currents, by the rotation of the Earth and the topography of the ocean floor, all combining to create paths that can carry icebergs thousands of kilometers from their origins. The primary force driving iceberg movement is ocean currents, the vast conveyor belts of water that circulate through the world's oceans, carrying heat and nutrients and everything that floats or swims, and icebergs, despite their enormous mass, are carried along by these currents like leaves in a stream, their movements determined more by the water around them than by their own momentum. In the Arctic Ocean and the North Atlantic, icebergs typically drift southward, carried by currents that flow from the polar regions toward the equator, and the most important of these currents is the Labrador Current, which flows south along the coast of Greenland and Labrador, carrying icebergs from Greenland's glaciers into the shipping lanes of the North Atlantic, where they pose a hazard to maritime traffic, and this is the region where the Titanic met its fate. Where the cold Labrador Current carrying icebergs meets the warm Gulf Stream carrying ships, creating a zone where ice and navigation intersect with sometimes tragic consequences. In the Antarctic, the situation is somewhat different, for the Antarctic continent is surrounded by the Antarctic Circumpolar Current, the largest ocean current in the world, flowing continuously from west to east around the entire continent, driven by the powerful westerly winds that blow in the latitudes around 60 degrees south. And this current tends to keep Antarctic icebergs circling around the continent rather than allowing them to drift northward into warmer waters. Though some icebergs do escape the circumpolar current and drift northward into the Atlantic, Pacific, or Indian Oceans, where they eventually melt in the warmer waters of lower latitudes. The movement of icebergs is not simply passive drift, for the wind also plays a significant role, particularly for icebergs with large portions extending above the water surface, and these icebergs act like sails, with the wind pushing against their exposed surfaces and adding to or counteracting the effect of currents, and this can cause icebergs to move in directions that seem to contradict the prevailing current. And it can cause icebergs in the same area to move in different directions if they have different shapes and different proportions of their mass above and below the waterline. The Coriolis effect, caused by Earth's rotation, also influences iceberg movement, causing objects moving across the surface of the rotating Earth to deflect to the right in the northern hemisphere and to the left in the southern hemisphere. And this effect is subtle for slow-moving objects like icebergs, but becomes significant over the long distances and time scales of iceberg drift, causing icebergs to curve gradually in their paths rather than moving in straight lines. Underwater topography of the ocean floor also affects iceberg movement, particularly for very large icebergs with deep keels that can scrape along the bottom in shallow waters. And this dragging can slow or stop an iceberg's movement, causing it to become grounded, sitting on the ocean floor while currents and winds flow around it. And grounded icebergs can remain in place for months or even years, slowly melting and rising until they become light enough to float free again and continue their journey. And these grounded icebergs can be hazards to submarine cables and pipelines, and can affect local ocean circulation by blocking currents and creating eddies. The speed of iceberg movement varies enormously, from nearly stationary for grounded icebergs or icebergs trapped in slow-moving waters, to speeds of several kilometers per day for icebergs caught in fast currents or pushed by strong winds. And over the course of months or years, this movement can carry icebergs from polar regions to latitudes where they are unexpected visitors, occasionally bringing them close to inhabited coastlines or into busy shipping lanes. And tracking the movement of these icebergs, predicting their paths, and warning ships and coastal communities of their presence is a complex task that involves satellite monitoring, aerial surveys, mathematical modeling of ocean currents and winds, and international cooperation among the nations whose waters icebergs might enter. The colors of ice. Let us drift now into one of the most beautiful and mysterious aspects of icebergs, their colors. For ice that appears white or clear in small quantities can display an extraordinary range of hues when formed into the massive structures of icebergs. And understanding these colors tells us about the structure and history of the ice. The most common color of icebergs is white, the white that comes from countless tiny air bubbles trapped within the ice, bubbles that scatter light in all directions, reflecting all wavelengths equally and giving the ice its characteristic bright white appearance. And this is the same reason that snow appears white despite being made of transparent ice crystals, the air gaps between and within the crystals scattering light diffusely. But compressed glacial ice, especially ice from deep within glaciers, where the weight of overlying ice has squeezed out many of the air bubbles, can appear blue, and this blue is not due to any coloring substance in the ice, but is an inherent property of the ice itself, caused by the way that water molecules absorb light. Water and ice absorb light preferentially at the red end of the spectrum, removing red wavelengths from white light passing through, and what remains is shifted toward the blue end of the spectrum. And this effect is very weak for small amounts of water or ice, which is why a glass of water appears clear, but it becomes noticeable when light passes through large volumes of clear ice. And the blue of glacial ice becomes visible when the ice is dense and clear enough that light penetrates deeply before being scattered back out, traveling through enough ice that the absorption of red light becomes significant. The most intense blues appear in the densest, oldest, most compressed ice from deep within glaciers that has been under pressure for thousands of years, ice that has lost almost all its air bubbles and has become almost perfectly clear. And when icebergs roll or carve in ways that expose this ancient ice, the blue can be startlingly vivid, an electric cerulean or turquoise that seems almost artificial in its intensity. And this blue ice is particularly common in crevasses and caves within icebergs, places where you are looking into the interior of the ice rather than at surfaces that have been weathered and whitened by exposure to air. Some icebergs display green colors, and the origin of green in icebergs is more complex and less well understood than the origin of blue, but it is thought to be related to the presence of organic matter, particularly phytoplankton or dissolved organic compounds that become incorporated into the ice, either from the glacier's base, where it scrapes along the ground and picks up sediment and dissolved materials, or from the ocean water itself, if ice forms in contact with water that contains high concentrations of organic material. And this green coloring is most common in Antarctic icebergs and is often seen in ice that appears to have formed or been modified in marine conditions rather than being purely glacial ice. Some icebergs and ice features display bands or layers of different colors, stripes running through the ice in patterns that can be horizontal or vertical or chaotically mixed. And these bands represent different layers of snow and ice that accumulated at different times and under different conditions, each layer capturing the atmospheric conditions and accumulation patterns of its era. And when these layers are exposed by carving or melting or weathering, they create visual records of climate history. Though reading these records requires careful analysis, for the layering in icebergs has often been deformed and folded by the flow of the glacier, distorting the original horizontal layers into complex curves and patterns. Black or brown colors in icebergs usually indicate the presence of rock dust and sediment, material that was either deposited on the glacier's surface by wind or avalanches, or was incorporated into the base of the glacier as it flowed over bedrock, grinding the rock into fine powder and mixing it into the ice. And this sediment can be distributed through the ice in distinct layers or bands, or can be more evenly mixed, giving the ice a darker, dirtier appearance. And while these sediment-rich icebergs may lack the pristine beauty of clear white or blue ice, they are scientifically valuable, for the sediments they carry can be analyzed to determine their origin and composition, providing information about the geology of the land over which the glacier flowed, and about the erosional processes that shape that landscape. Life and death on ice. As we drift through our exploration, let us now consider the icebergs not as isolated objects, but as ecosystems, as temporary floating islands that support life in the otherwise relatively barren open ocean. For icebergs carry with them not just water but nutrients, minerals, and sometimes even living organisms. And as they melt, they transform the waters around them, creating localized environments that can bloom with biological activity. The process begins with the melting of the iceberg, which releases fresh water into the surrounding ocean. And this fresh water is not pure H2O, but contains dissolved minerals and nutrients that were locked into the ice when it formed, including iron, which is a limiting nutrient in many ocean regions, particularly in the Southern Ocean around Antarctica, where surface waters are rich in nitrogen and phosphorus but poor in iron, and this iron limitation restricts the growth of phytoplankton, the microscopic plant-like organisms that form the base of the marine food web. And when an iceberg melts and releases iron-rich water, it can stimulate a phytoplankton bloom in its wake, a burst of biological productivity that can be detected from satellites as an area of increased chlorophyll concentration. A green spreading out from the iceberg's position as the phytoplankton multiply in response to the newly available nutrients. These iceberg-induced blooms can be substantial, with icebergs acting as fertilizers for the ocean, supporting not just phytoplankton, but the entire food chain that depends on phytoplankton. From the tiny zooplankton that graze on the phytoplankton to the fish and krill that eat the zooplankton to the whales and seabirds and seals that eat the fish and krill, all benefiting from the nutrients released by the melting ice. And this connection between icebergs and ocean productivity is a reminder of how interconnected Earth systems are, how the ice sheets and glaciers of the polar regions, through the icebergs they produce, can influence the biological productivity of vast areas of ocean far from the poles. Beyond their role as nutrient sources, icebergs also provide physical habitat, and the surfaces of icebergs, both above and below the waterline, can support diverse communities of organisms. Seals, particularly species like craybater seals and leopard seals in the Antarctic, often haul out onto icebergs to rest, to escape from predators in the water, or to give birth and raise their pups. And these icebergs serve as temporary haul-out sites, drifting platforms that the seals can use as bases for hunting and resting, though the seals must be adaptable. Ready to enter the water and swim to another iceberg if their current ice platform becomes unstable or drifts into unsuitable waters. Penguins also use icebergs, particularly Adelie penguins and chinstrap penguins and other species that live in the Antarctic, hopping onto icebergs to rest between foraging trips, using them as lookout posts from which to scan for predators, and sometimes even nesting on large, stable icebergs that have grounded near shore. Below the waterline, the surfaces of icebergs can be colonized by algae and bacteria and other microorganisms that can tolerate the cold conditions and that can attach to the ice or to particles embedded in the ice. And these microbial communities form the base of a small but complex food web that exists on and within the iceberg itself, with small invertebrates grazing on the microorganisms and in turn being eaten by fish and larger predators. The meltwater from icebergs creates plumes of cold, fresh water that can extend for kilometers, and these plumes have different temperature and salinity characteristics than the surrounding ocean water, creating stratification and affecting how nutrients and organisms are distributed vertically in the water column. And the boundaries between these different water masses can be zones of enhanced biological activity, where organisms congregate to feed on the concentrations of plankton and nutrients that accumulate at density transitions. As icebergs melt and break apart, they leave behind fields of smaller ice pieces, from burgy bits and growlers down to small fragments called brash ice. And these ice fields create physical structure in the water, providing shelter for small organisms, reflecting light and sound in ways that affect how predators hunt and how prey hide, and creating a patchwork of microenvironments, each with its own characteristics and its own community of organisms. Sound beneath the ice. Let us drift deeper now into the acoustic world of icebergs, for these silent wanderers are not truly silent, but produce a symphony of sounds, some of which can be heard by the unaided human ear, others of which require sensitive underwater microphones to detect. And listening to icebergs, understanding the sounds they make and what those sounds tell us, has become an important tool for monitoring ice and ocean conditions. The most obvious sounds are those made during calving, the crack and roar as ice breaks free from glaciers, sounds that can be extraordinarily loud, comparable to thunder or to explosions, and these sounds can travel for kilometers through air and through water, carrying energy that shakes the ground and creates waves in the ocean. And for researchers monitoring glaciers, the sound of calving events provides information about the frequency and size of ice loss, helping to quantify how fast glaciers are melting and how much ice is entering the ocean. But icebergs continue to make sounds long after they have calved, and these sounds are more subtle, more varied, and in some ways more interesting than the dramatic sounds of calving. As icebergs melt, they produce a characteristic crackling or fizzing sound, the Berge-Seltzer mentioned earlier, caused by the release of air bubbles that have been compressed in the ice for thousands of years. And when these bubbles escape, they create tiny pops and hisses that collectively sound like a carbonated beverage. And this sound is most intense near the surface of the iceberg, where melting is most rapid, and it can be heard both in air and underwater. A constant, gentle noise that pervades the waters around melting ice. Icebergs also crack and groan as they adjust to temperature changes, as stresses build up from uneven melting or from currents and waves pushing against them. And these sounds can range from quiet creaks to loud cracks that sound like gunshots. And the frequency and intensity of these sounds provides information about the internal structure of the ice and about the forces acting on it. And researchers studying these sounds can sometimes predict when an iceberg is likely to roll or break apart based on the patterns of acoustic activity. When icebergs collide with each other or scrape against the seafloor, they produce grinding and bumping sounds that can be very low frequency, almost below the range of human hearing, but detectable by sensitive instruments. And these low-frequency sounds can travel for hundreds or even thousands of kilometers through the ocean. For low-frequency sound propagates very efficiently in water, and by listening to these sounds with networks of underwater microphones called hydrophones, scientists can track the movement and behavior of icebergs across vast areas of ocean without needing to observe them directly. The underwater sounds of icebergs also contribute to the ambient noise of the ocean, the background soundscape against which marine animals must communicate and navigate. And in polar regions where icebergs are common, this acoustic contribution can be significant, potentially affecting how whales and seals and other marine mammals use sound, though the extent of these effects is not yet fully understood and is an active area of research. The study of iceberg sounds, called cryocoustics, is a growing field that combines glaciology, oceanography, acoustics, and signal processing, and it has applications beyond simply monitoring icebergs. For the sounds of ice can also provide information about ocean conditions, about the presence of marine life, about underwater volcanoes and earthquakes, about changes in water temperature and salinity that affect how sound travels, and about the health of coral reefs and other ecosystems that produce their own characteristic sounds. By deploying networks of hydrophones in polar waters and analyzing the sounds they detect, researchers are building a more complete picture of the acoustic environment of the oceans, understanding how sound is produced, how it propagates, and how it is used by both natural processes and by the organisms that inhabit the seas. And this understanding is becoming increasingly important as human activities, particularly shipping and offshore industry, add more and more noise to the ocean, potentially interfering with natural acoustic communication and navigation. melting, and transformation. As we continue our gentle drift through the life cycle of icebergs, let us now explore in detail the process of melting, for this is how icebergs ultimately meet their end, slowly dissolving into the ocean from which they are composed, but which they had left for a time in frozen form. Iceberg melting occurs through multiple mechanisms, each contributing to the gradual reduction of the ice mass, and the relative importance of these mechanisms depends on the size and shape of the iceberg, on the temperature and salinity of the surrounding air and water, on the intensity of solar radiation, and on the mechanical action of waves and currents. The most straightforward mechanism is thermal melting, the transfer of heat from the warmer environment to the colder ice, causing the ice to undergo a phase transition from solid to liquid, and this heat transfer occurs at all surfaces of the iceberg. From the air at the upper surfaces, from the water at the waterline and below, and even from solar radiation that penetrates into the ice before being absorbed and converted to heat. Air temperatures in polar regions are often below freezing, especially in winter, and in these conditions, icebergs may actually grow slightly as spray and waves freeze onto their surfaces. But in summer, when air temperatures rise above freezing, especially in regions where icebergs have drifted to lower latitudes, the upper surfaces of icebergs melt, forming pools of fresh water on top of the ice, and these melt pools can be quite deep, becoming lakes perched on the iceberg surface. And the presence of these pools affects the iceberg's stability and can accelerate melting, for water has a lower albedo than ice, meaning it absorbs more solar radiation rather than reflecting it, and this absorbed energy warms the water, which then melts the ice at the bottom of the pool, deepening it further in a positive feedback loop. Melting below the waterline is generally faster than melting above, for ocean water, even in polar regions, is typically warmer than the ice, and water is a much more efficient conductor of heat than air, allowing heat to be transferred to the ice more rapidly, and this differential melting causes icebergs to develop distinctive shapes, with the underwater portions melting back faster than the portions above water, creating overhangs and undercuts, and these features can make icebergs unstable. For if too much mass is removed from below, the center of buoyancy shifts, and the iceberg may roll to find a new equilibrium. Wave action contributes to melting and erosion at the waterline, where the repeated rise and fall of waves creates mechanical stress that breaks off pieces of ice, and the turbulence of wave action brings warmer water into contact with the ice more effectively than calm water would, increasing the rate of heat transfer, and over time, this wave erosion creates a notch in the iceberg at the waterline, a horizontal groove that circles the iceberg, and as this notch deepens, the structural integrity of the iceberg is compromised, and large sections of the ice above the waterline may carve off, falling into the sea and creating new smaller icebergs or burgy bits. Solar radiation penetrates into clear ice and is absorbed in the interior, creating internal melting that can form hollow areas or channels within the iceberg, and these internal voids can fill with water or can remain air-filled, and their presence affects the iceberg's strength and stability, for ice with internal voids is more brittle and more prone to fracturing than solid ice. The rate of melting varies enormously depending on conditions, and a small iceberg in relatively warm water might melt completely in a matter of days or weeks, while a large tabular iceberg in cold Antarctic waters might persist for years or even decades, slowly wasting away but remaining a substantial presence in the ocean throughout its long life. As icebergs melt, they do not simply get smaller while maintaining their shape, but undergo continuous transformation, their shapes evolving as different parts melt at different rates, as pieces break off, as they roll and rotate, and tracking this evolution, understanding the physics that govern it, and predicting how long an iceberg will last, and how it will change are important for maritime safety, and for understanding the contribution of icebergs to ocean freshwater budgets and nutrient cycles. The final stages of an iceberg's life are often the most rapid, for as the iceberg shrinks, its ratio of surface area to volume increases, meaning there is more surface through which heat can be transferred relative to the amount of ice remaining, and this accelerates melting, and small remnants of once massive icebergs can melt away in a matter of hours or days, disappearing into the ocean without trace, the ancient ice returning to the water cycle. The minerals and nutrients locked in the ice released to nourish ocean life. The air bubbles containing samples of ancient atmosphere released to mix with the modern air, the entire structure dissolving as if it had never been, leaving only memories and perhaps photographs, and the data recorded by researchers who studied it during its journey. Icebergs through human history. Let us drift now through the centuries of human interaction with icebergs, for these floating mountains of ice have captured human imagination, have been hazards to navigation, have been sources of fresh water and wonder, and have played roles in exploration, commerce, disaster, and science. The indigenous peoples of the Arctic, the Inuit and other groups who have lived in polar regions for thousands of years, have intimate knowledge of sea ice and icebergs, understanding their behavior, using them as landmarks for navigation, hunting seals and whales and other animals around them, and incorporating them into their culture and mythology, and this traditional knowledge, passed down through generations, includes observations and insights about ice that are only now being documented and appreciated by Western science. European explorers who ventured into Arctic and Antarctic waters encountered icebergs with a mixture of awe and fear, for these massive structures, often appearing suddenly out of fog or darkness, posed grave dangers to wooden sailing ships, and many expeditions suffered damage or loss from collisions with ice. And the accounts of these explorers, their descriptions of icebergs, and their attempts to navigate safely through ice-filled waters, provide historical records of ice conditions and distribution that are valuable for understanding how ice coverage has changed over time. The whaling industry, which operated extensively in polar and subpolar waters during the 18th and 19th centuries, had to contend with icebergs as a regular hazard, and whalers developed techniques for navigating through ice, for identifying dangerous ice formations, and for using ice as shelter from storms or as sources of fresh water, melting ice to replenish their ships' water supplies. And the logs and journals of whaling ships contain observations of ice and icebergs that contribute to our historical understanding of ice conditions. The age of steamships and large passenger liners in the late 19th and early 20th centuries brought with it new dangers from icebergs. For these large, fast ships, traveling on regular schedules between Europe and North America, often crossed the North Atlantic during seasons when icebergs were present, and the pressure to maintain schedules and the confidence in the strength of steel-hulled ships led to risks being taken. ships proceeding at full speed through areas where ice was known or suspected to be present. And the most famous and tragic result of this was the sinking of the RMS Titanic on April 15, 1912, when the supposedly unsinkable ship struck an iceberg on its maiden voyage from Southampton to New York, and in less than 3 hours sank, taking with it over 1,500 passengers and crew in one of the deadliest peacetime maritime disasters in history. The Titanic disaster had profound effects on maritime safety, leading directly to the first International Convention for the Safety of Life at Sea in 1914, which established new requirements for lifeboats, for radio communications, for watertight compartments and other safety features, and also led to the formation of the International Ice Patrol, operated by the United States Coast Guard, which monitors iceberg conditions in the North Atlantic and provides warnings to ships. Using ships and aircraft and satellites to track icebergs, to predict their movements, and to define areas where ice is present or likely to be encountered. And since the Ice Patrol began operations, no ship heeding its warnings has been lost to iceberg collision, a remarkable safety record that has prevented countless potential disasters. Scientific study of icebergs began in earnest in the 20th century, as glaciologists and oceanographers recognized that icebergs were not just hazards to navigation, but were important components of polar environments, affecting ocean circulation and chemistry, providing habitats for marine life, and carrying valuable information about past climates locked in their ice. And research programs were established to study icebergs systematically, to understand their formation and evolution, their movement patterns, their melting rates, and their effects on the ocean. And this research continues today, using ever more sophisticated tools from satellite, remote sensing to underwater robots, to genetic analysis of the organisms that live on and around icebergs. The great tabular giants of Antarctica. As we drift deeper into the realm of extraordinary ice, let us focus our attention on the largest icebergs in the world, the tabular giants that carve from the ice shelves of Antarctica, some of which are so vast that they rival small countries in area, floating ice islands that persist for years or decades, slowly drifting through the Southern Ocean, occasionally making headlines when they break free or collide with other features. These enormous icebergs, given alphanumeric names by the National Ice Center that tracks them, can be hundreds of kilometers long, tens of kilometers wide, and hundreds of meters thick, containing trillions of tons of ice, enough fresh water to supply entire nations for years. And their sheer scale is difficult to comprehend, for we are accustomed to thinking of icebergs as isolated objects that a ship can sail around in minutes. But these tabular behemoths are more like floating territories, taking days to circumnavigate and visible from space as distinct white patches in the dark ocean. The carving events that produce these giants are among the most dramatic natural phenomena on Earth, with sections of ice shelf hundreds of meters thick and hundreds of kilometers long suddenly breaking free, the separation often occurring along pre-existing cracks and rifts in the ice shelf that have been growing for years or decades, slowly propagating through the ice until finally they reach a critical length and the section of shelf breaks away, a process that can take days or weeks, with the crack extending kilometer by kilometer until finally the separation is complete and a new iceberg begins its independent existence. One of the most closely watched recent examples was Iceberg B-15, which carved from the Ross Ice Shelf in Antarctica in March of 2000, and at the time of carving, it measured approximately 300 kilometers long and 40 kilometers wide, with an area of about 11,000 square kilometers, roughly the size of the island of Jamaica, and this made it the largest iceberg ever recorded by satellites. Though historical records suggest that even larger bergs may have existed in the past. B-15 did not remain a single piece, but over the following years broke into smaller sections, designated B-15A, B-15B, and so on, and these fragments drifted through the Ross Sea, some of them grounding on underwater features, others drifting further into the Southern Ocean, and researchers tracked their movements and monitored their decay, using them as natural experiments to study iceberg behavior and ocean conditions. Another notable giant was Iceberg A68, which carved from the Larsen Sea ice shelf on the Antarctic Peninsula in July of 2017, and this berg measured approximately 170 kilometers long and 50 kilometers wide, with an area of about 6,000 square kilometers, and it drifted northward from the Antarctic Peninsula, gradually breaking into smaller pieces and raising concerns that it might collide with South Georgia Island, potentially disrupting the island's marine ecosystems. But ultimately the berg broke apart before reaching the island, its fragments dispersing and melting in the warmer waters of the South Atlantic. These giant tabular icebergs have significant effects on their surroundings, for they are large enough to affect ocean circulation, blocking currents, creating eddies and gyres, altering the distribution of sea ice and the access of marine mammals and penguins to open water. And when they ground on shallow seafloor features, they can remain in place for years, becoming semi-permanent fixtures that affect local conditions. Ice shelves from which these giants carve are themselves fascinating and important features, floating extensions of the Antarctic ice sheet that rest on the ocean, but remain connected to the grounded ice on land, and these shelves play a crucial role in stabilizing the ice sheet, acting as buttresses that slow the flow of ice from the interior of the continent to the ocean. And when large sections of ice shelf carve away, the remaining shelf becomes less stable, and the glaciers feeding into it can accelerate, increasing the rate at which ice flows from land into the ocean, contributing to sea level rise. And this connection between ice shelf stability, iceberg carving, and sea level rise is a major focus of current research in glaciology and climate science. For understanding and predicting these processes is essential to projecting future sea level changes and their impacts on coastal communities around the world. The iceberg harvest. Let us drift now into more speculative and creative territory, exploring ideas that humans have had about using icebergs as resources. For the vast quantities of fresh water locked in icebergs have long inspired proposals to harvest this water and transport it to regions suffering from water scarcity. The idea of towing icebergs to arid regions is not new, appearing in various forms throughout the 20th century, and the basic concept is straightforward. Identify an iceberg of suitable size, attach towing equipment, and use ships or other means to pull the iceberg to a destination where the water is needed, and along the way and upon arrival, harvest the meltwater, using it for drinking water, agriculture, or other purposes. The appeal of this idea is obvious, for icebergs contain enormous quantities of pure fresh water, water that is not contaminated by industrial pollutants or agricultural runoff, water that was frozen thousands of years ago and has been preserved in pristine condition, and moving this water to where it is needed seems more straightforward than desalination or other water generation technologies. But the practical challenges are enormous and have so far prevented any large-scale implementation of iceberg harvesting. The first challenge is simply selecting an appropriate iceberg, for it must be large enough to justify the cost and effort of towing, but not so large that it cannot be moved, and it must have a shape that is stable and that presents a profile suitable for towing, avoiding shapes that would cause the iceberg to roll or break apart during transport. And it must be located in a position where it can be accessed by towing vessels, and where ocean currents and winds are favorable for the intended route. Once an iceberg is selected, the next challenge is attaching towing equipment, and various proposals have suggested wrapping icebergs in nets or fabric to hold them together, and to provide attachment points for tow lines, or drilling into the ice to install anchors or bollards, or encasing the iceberg in some kind of insulating jacket that would slow melting during the journey while also providing structural reinforcement. The towing itself would be slow and expensive, requiring powerful vessels and consuming vast amounts of fuel. For even though icebergs float and do not need to be lifted, they have enormous mass and inertia, and overcoming ocean currents and winds to move an iceberg across thousands of kilometers of ocean would be a major undertaking, likely taking weeks or months. And during this time, the iceberg would be continuously melting, losing mass and potentially breaking apart, reducing the amount of water that actually reaches the destination. Various studies and proposals have been made over the years, including a notable effort in the 1970s by a Saudi prince who investigated the feasibility of towing icebergs from Antarctica to the Arabian Peninsula. And while that particular project was never implemented, it generated significant interest and led to research into the engineering and economic aspects of iceberg transport. And some of this research suggested that under certain conditions, particularly for relatively short distances, and with advances in towing technology and in methods for insulating icebergs during transport, the idea might be economically viable, though it would still face significant environmental and regulatory challenges. More recently, there have been proposals to use icebergs as freshwater sources on a smaller scale, not towing entire icebergs across oceans, but instead harvesting ice from icebergs that drift near water-stressed regions, capturing meltwater or breaking off pieces of ice to be processed. And some limited experimental efforts along these lines have been undertaken. For example, in Newfoundland, where a company has been harvesting small amounts of iceberg ice to sell as ultra-premium bottled water, marketing it as the purest water on Earth, sourced from icebergs that are thousands of years old. And while this is a niche luxury product rather than a solution to water scarcity, it demonstrates that iceberg ice can be harvested and commercialized, even if scaling up to meet significant water needs remains a distant prospect. Climate records in ice. As we continue our gentle drift through the mysteries of icebergs, let us explore one of their most scientifically valuable aspects: the fact that the ice of which they are composed is not just frozen water, but is also an archive, a physical record of Earth's climate history extending back through thousands or even hundreds of thousands of years. And reading this archive, extracting and interpreting the information locked in the ice, has revolutionized our understanding of past climates and of the natural variability of Earth's climate system. The key to ice as a climate archive is the layering that occurs as snow accumulates year after year on ice sheets and glaciers, each layer of snow recording the atmospheric conditions at the time it fell, the temperature, the atmospheric composition, the amount of snowfall, the presence of dust or volcanic ash or other materials that were in the atmosphere. And as these layers are buried by subsequent snowfall, they are compressed into ice, and the layering is preserved, creating a stratigraphy similar to the layering in sedimentary rocks, but made of ice instead of stone. By drilling cores through ice sheets, extracting long cylinders of ice that sample the entire depth of the ice from surface to bedrock, scientists can access this layered archive and can analyze each layer to reconstruct past conditions. And ice cores from Greenland and Antarctica have been drilled to depths of over 3 kilometers, reaching ice that is over 800,000 years old, providing a continuous record of climate spanning multiple glacial interglacial cycles. The information contained in ice cores is remarkably diverse and detailed, including the isotopic composition of the water molecules themselves, which provides information about temperature, for the ratios of heavy to light isotopes of hydrogen and oxygen in water vary with the temperature at which the water evaporated and the temperature at which the snow formed. And by measuring these isotopic ratios in the ice, scientists can estimate past temperatures with considerable precision. The air bubbles trapped in the ice contain samples of ancient atmosphere, with the same composition of gases that existed when the bubbles were sealed, and by extracting these bubbles and analyzing the gases they contain, scientists can measure past concentrations of carbon dioxide, methane, nitrous oxide, and other greenhouse gases, and this has provided definitive evidence that current atmospheric CO2 levels, over 400 parts per million, are higher than at any time in at least the past 800,000 years, and that the increase in CO2 and other greenhouse gases over the past 2 centuries, since the beginning of the Industrial Revolution, is unprecedented in the ice core record and is directly linked to human activities. The ice also contains dust and ash and other particles that were in the atmosphere when the snow fell, and analyzing these materials provides information about volcanic eruptions, about the extent of deserts and the strength of winds transporting dust, about biomass burning and other sources of aerosols, and about changes in atmospheric circulation patterns. Icebergs, because they are pieces of glaciers and ice sheets, carry this climate record with them as they drift through the ocean. And while it is challenging to extract ice cores from drifting icebergs, and the ice in icebergs has often been deformed and mixed by the flow of the glacier, making its layering less clear than in the undisturbed ice of ice sheets, icebergs still contain valuable climate information, and some researchers have proposed that icebergs could be used as mobile platforms for climate research, allowing sampling of ice from glaciers that are difficult to access by land, and that the melting of icebergs gradually releases this ancient climate information into the ocean, the trapped gases bubbling out, the dust and other particles settling to the seafloor, becoming part of marine sediments, creating secondary archives that can be sampled and studied. And this connection between ice archives and marine sediment archives is an active area of research, for by combining information from both sources, scientists can build more complete pictures of past climate and can better understand the mechanisms and feedbacks that drive climate change. Icebergs and sea level. Let us now drift into the relationship between icebergs and sea level, for this relationship is often misunderstood, and clarifying it helps us understand both the immediate and long-term impacts of ice on the ocean. A common misconception is that melting icebergs contribute directly to sea level rise, but this is not correct, for icebergs are already floating in the ocean, and when they melt, the water they produce simply takes the place of the water they were displacing, and the net effect on sea level is zero. This principle is a consequence of Archimedes' principle, which states that a floating object displaces a volume of water whose weight equals the weight of the object. And because ice is less dense than water, an iceberg floats with part of its volume above the waterline. But the volume of water displaced by the underwater portion has the same mass as the entire iceberg, including the portion above water. And when the iceberg melts, it produces exactly that volume of water. And so the sea level does not change. This can be verified with a simple experiment. Fill a glass with water, add ice cubes that float partially submerged, mark the water level, and then wait for the ice to melt completely, and you will find that the water level remains at the mark, unchanged by the melting ice, and the same principle applies to icebergs in the ocean, no matter how large they are. However, this does not mean that icebergs are irrelevant to sea level. For the processes that produce icebergs, the carving of ice from glaciers and ice sheets is part of the mechanism by which ice that is on land enters the ocean. And it is this transfer of ice from land to ocean that does contribute to sea level rise. Ice that is sitting on land, on Greenland or Antarctica or in mountain glaciers, is not displacing ocean water. And when this ice flows into the ocean and either floats as an ice shelf or breaks off as icebergs, it adds new water to the ocean, increasing its total volume and raising sea level. And the melting of the iceberg that occurs subsequently is irrelevant to sea level, because the water from that melted iceberg is already in the ocean, already counted in the sea level budget. The distinction is subtle but important. The carving of icebergs from land-based ice contributes to sea level rise, but the melting of icebergs that are already floating does not. And understanding this distinction is essential to understanding the contributions of different ice reservoirs to sea level change. Antarctica and Greenland together contain enough ice that if all of it melted, sea levels would rise by over 60 meters, inundating most coastal cities and dramatically reshaping the world's coastlines. And while such complete melting is not expected to occur in the near future, even partial melting and the acceleration of ice discharge through increased carving and iceberg production could raise sea levels by meters over the coming centuries, affecting billions of people who live in coastal areas. The rate at which ice is currently being lost from Greenland and Antarctica has been increasing, driven by warming air and ocean temperatures, and satellite measurements and aerial surveys show that glaciers are thinning, ice shelves are retreating, and the rate of iceberg carving is increasing, all indicators that the ice sheets are losing mass, and the meltwater from these ice sheets, both from surface melting and from the melting of icebergs, is entering the ocean, contributing to observed sea level rise, which has been about 3 millimeters per year on average over the past few decades, but is accelerating, with recent measurements showing rates closer to 4 millimeters per year, and projections suggest that this rate will continue to increase as warming continues. The future of icebergs and ice sheets is thus intimately connected to the future of sea level and to the fate of coastal communities, and understanding and predicting ice sheet behavior, including the production and fate of icebergs, is one of the major challenges in climate science today, requiring sophisticated models that simulate ice flow, calving processes, ocean-ice interactions, and the feedbacks between ice, ocean, and atmosphere that determine how quickly ice sheets will respond to warming. The poetry of impermanence. As we drift into more contemplative territory, let us reflect on the symbolic and aesthetic dimensions of icebergs, for beyond their scientific interest and their practical importance, icebergs are objects of profound beauty and have captured the imaginations of artists, writers, photographers, and travelers. Representing in their cold grandeur themes of impermanence, isolation, hidden depths, and the sublime power of nature. Image of the iceberg has entered human culture as a metaphor, most famously in the phrase "tip of the iceberg," used to describe situations where what is visible represents only a small fraction of a larger hidden reality. And this metaphor resonates because it captures a truth not just about icebergs, but about many aspects of life and knowledge, that surface appearances can be misleading, that understanding requires looking beneath the obvious, that depth and complexity hide beneath simplicity. Icebergs also embody impermanence in a particularly vivid way, for they are massive, seemingly permanent structures, yet they are in fact transient, melting continuously, destined to disappear back into the ocean within years or at most decades. And this combination of apparent permanence with inevitable dissolution makes them powerful symbols of change and mortality, reminders that nothing lasts forever, that all structures, no matter how solid they seem, are temporary arrangements that will eventually return to their constituent elements. The aesthetics of icebergs have inspired countless works of art, from paintings and photographs capturing their forms and colors to poetry and prose exploring their meanings. And to encounter an iceberg in person, to see these enormous structures floating in polar waters, is often described as a deeply moving experience, an encounter with the sublime, that quality identified by philosophers and aestheticians as arising from experiences of vastness, power, and beauty that exceed our ability to fully comprehend or control, producing a mixture of awe, wonder, and perhaps a tinge of fear. The silence and stillness of icebergs, drifting slowly through calm waters, creates a sense of timelessness, a feeling that these frozen mountains exist outside the normal flow of human time, following rhythms set by geology and climate rather than by clocks and calendars. And this otherworldly quality makes them seem almost like visitors from another world, messengers from the deep past carrying ice that formed when the world was different, when humans did not yet exist or existed in very different circumstances. And this connection to deep time, to scales of years and centuries and millennia that far exceed human lifespans, gives icebergs a kind of dignity, a gravitas that speaks to something fundamental about Earth and existence and change. Photographers particularly are drawn to icebergs, for they present endless compositional possibilities, their forms constantly changing as they melt and rotate, their colors shifting with light and weather, their textures ranging from smooth and glassy to rough and fractured, and the interplay of ice and water and sky creates scenes of stark beauty. And the best iceberg photographs capture not just the physical appearance of the ice, but something of its character, its presence, its meaning. And these images circulate widely, appearing in galleries and magazines and online, bringing the experience of icebergs to people who may never visit polar regions, but who can still appreciate these frozen giants through the photographer's lens. Writers too have been inspired by icebergs, using them as settings for stories, as symbols in poems, as subjects of essays exploring themes of nature, time, beauty, and human relationship to the non-human world. And some of the most memorable writing about icebergs comes from explorers and sailors who encountered them at sea, their accounts mixing practical observations about ice conditions with lyrical descriptions of the beauty and terror of navigating through ice-filled waters. And these historical accounts provide not just information about past ice conditions, but also insight into how people experienced and understood icebergs in different eras. Technological eyes on ice. Let us drift now into the present day, exploring how modern technology has transformed our ability to observe and understand icebergs. For satellites and aircraft and ships equipped with sophisticated sensors now monitor icebergs continuously, tracking their positions, measuring their sizes, observing their changes, and this data feeds into models and systems that provide warnings and forecasts, making modern navigation much safer than it was in the past and enabling research that was previously impossible. Satellite remote sensing is perhaps the most important tool, for satellites in orbit around Earth can observe vast areas of ocean, detecting icebergs by the contrast between ice and water in optical images or by the distinctive radar signatures that ice produces. And because satellites pass over the same regions repeatedly, they can track icebergs over time, documenting their movements and their evolution, and this capability has been transformative for iceberg monitoring, allowing systematic global observation that would be impossible from ships or aircraft alone. Several different types of satellite sensors are used for iceberg detection and monitoring. Optical sensors capture images similar to photographs, showing icebergs as white or light-colored features against the dark ocean, and these work well in daylight and clear weather, but are limited by clouds and by darkness. Radar sensors emit microwave pulses and measure the reflections, and because microwaves penetrate clouds and do not require sunlight, radar can observe icebergs day or night in any weather, making it especially valuable for monitoring polar regions where clouds are common and where winter darkness lasts for months. And thermal infrared sensors detect heat radiation, and because ice is colder than water, icebergs appear as cold features against the warmer ocean background, providing another way to detect and track them. In addition to satellites, aircraft are used for iceberg reconnaissance, particularly by the International Ice Patrol, which operates regular flights over the North Atlantic during iceberg season, typically from February through July, flying patterns that survey the areas where icebergs are most likely to be encountered by ships. And these aircraft use visual observation, radar, and other sensors to detect icebergs, and the data collected is immediately transmitted to ships and to maritime authorities, providing up-to-date information about ice conditions. And the Ice Patrol also uses this data to model iceberg movements, combining observed positions with information about ocean currents and winds to forecast where icebergs will drift in the coming days, allowing ships to plan routes that avoid ice. Ships themselves also carry ice detection equipment, with modern vessels being equipped with radar systems that can detect ice ahead, and with forward-looking sonar that can detect underwater ice, reducing the risk of collision. And some research vessels carry specialized equipment for studying icebergs up close, including multi-beam sonar systems that can map the underwater shape of icebergs, autonomous underwater vehicles that can swim beneath icebergs to observe their keels, and coring equipment that can extract samples of ice for laboratory analysis. Beyond detection and tracking, satellites and other remote sensing platforms also measure properties of icebergs that are important for understanding their behavior and their impacts, including their thickness, their temperature, their rates of melting, and the characteristics of the water around them. And this information feeds into scientific studies of ice-ocean interactions, of the contribution of icebergs to ocean freshwater budgets and nutrient cycles, and of the response of ice sheets and glaciers to climate change. The data collected by all these sensors is enormous in volume, requiring sophisticated data processing and analysis methods, including machine learning and artificial intelligence algorithms that can automatically detect icebergs in satellite images, distinguish them from sea ice and from other features, and track them as they move and change. And these automated systems are becoming increasingly capable, reducing the need for human analysts to manually review every image and allowing monitoring systems to process data from multiple satellites simultaneously, providing a more complete and timely picture of ice conditions than was ever before possible. The microbial frontier. As we drift into even more hidden realms, let us explore the microscopic life that exists on and within icebergs. For these frozen structures are not sterile, but host diverse communities of microorganisms, bacteria and archaea and fungi and algae that have adapted to survive in the extreme cold and that play important roles in biogeochemical cycles, contributing to the processing of nutrients and organic matter and to the transformation of the ice itself. The study of iceberg microbiology is a relatively young field, for it requires specialized sampling techniques and equipment to collect ice and water from icebergs without contaminating them, and to keep samples frozen or cold during transport to laboratories where they can be analyzed. But research over the past few decades has revealed that icebergs are far from lifeless, that their surfaces and interiors contain viable microorganisms, some of which are active and metabolizing even at temperatures well below freezing. And that these microorganisms represent a poorly understood component of polar ecosystems. The origins of iceberg microbes are diverse. Some are incorporated into the ice at the time it forms in glaciers, captured from the air or from the glacier surface or from the glacier bed where it contacts rock and sediment. Some colonize the ice after it calves, with microorganisms from seawater attaching to the ice surfaces or entering cracks and melt channels, and some may be transporting onto icebergs by wind or by animals that rest on the ice. The conditions within and on icebergs are extreme by the standards of most life, with temperatures often below freezing, high salinity in briny pockets where salt has been excluded from ice crystals, high levels of ultraviolet radiation on exposed surfaces, limited nutrients, and for internal microbes, complete darkness and isolation from the external environment. And yet microorganisms have evolved strategies to cope with all these stresses, producing antifreeze proteins that prevent ice crystals from forming inside their cells, entering dormant states when conditions are too severe for active metabolism, and employing enzymes that function at low temperatures. And these adaptations make iceberg microbes of great interest to astrobiologists studying the possibility of life on frozen worlds elsewhere in the solar system. For if life can exist in the ice of Earth's icebergs, then perhaps similar life could exist in the ice of Jupiter's moon, Europa, or Saturn's moon Enceladus, or other icy bodies where conditions may be similar. The ecological roles of iceberg microbes are still being elucidated, but it appears that they contribute to nutrient cycling, breaking down organic matter trapped in the ice, converting nitrogen and sulfur compounds between different chemical forms, and producing compounds that can be used by other organisms. And as icebergs melt, these microbes are released into the surrounding water, where they can seed microbial communities, contribute to local biodiversity, and potentially affect larger-scale ocean processes if released in sufficient quantities. Some iceberg microbes are also photosynthetic, particularly algae that grow on the surfaces of icebergs or in meltwater pools on top of icebergs, and these photosynthesizers contribute to primary productivity, converting sunlight and carbon dioxide into organic matter, and they can color the ice, creating green or red or brown patches or layers where algae are dense, and these colored patches absorb more sunlight than white ice does, potentially accelerating melting through a feedback similar to the one that occurs with melt pools. And this connection between microbial communities and ice albedo is an interesting aspect of ice-climate interactions that is only beginning to be studied. The DNA sequences of iceberg microbes reveal connections to microorganisms from other environments, sometimes showing close relationships to soil bacteria or to microbes from deep subsurface environments, suggesting that glacier ice and icebergs are connected to a broader microbial world, serving as repositories of microbial diversity that has been isolated for long periods, but that can be revitalized when ice melts. And genetic analysis of ancient ice from deep ice cores has revealed microbes that have been frozen for hundreds of thousands of years, and that can sometimes be revived when the ice is melted under sterile conditions, demonstrating the remarkable resilience of microbial life and the potential for frozen environments to preserve viable organisms over geological timescales. Icebergs in art and imagination. Let us drift into the realm of human creativity and explore how icebergs have been represented and reimagined in various forms of art and cultural expression. For these frozen forms have provided inspiration and subject matter for artists working in diverse media and traditions. In visual art, icebergs have been painted by artists ranging from 19th century explorers who documented their expeditions with watercolors and sketches to contemporary painters creating large-scale abstractions inspired by ice formations. And these artworks capture different aspects of icebergs: their monumentality, their ethereal beauty, their strangeness, their place in sublime landscapes of ice and ocean and sky. The Hudson River School painter Frederick Edwin Church created several notable iceberg paintings in the 1860s and 70s, after traveling to the Arctic and witnessing icebergs firsthand, and his paintings, such as the Icebergs from 1861, depict these structures with meticulous detail and dramatic lighting, conveying both the physical reality of the ice and a sense of the spiritual or transcendent experience of encountering such natural wonders. Photography has produced some of the most striking iceberg imagery, with photographers using the medium's capacity for precise documentation to capture the forms and textures of ice. And the best iceberg photographs balance documentary accuracy with aesthetic sensibility, using composition, light, color, and framing to create images that are both informative and beautiful, and the work of photographers like James Balog, whose extreme ice survey has documented changing glaciers and icebergs over decades, combines scientific purpose with artistic achievement, creating photographs that communicate urgency about climate change while also celebrating the beauty of ice. In literature, icebergs appear in both fictional and non-fictional contexts, serving as settings, symbols, and subjects. Ernest Hemingway famously used the iceberg as a metaphor for his writing style, the iceberg theory, or theory of omission, suggesting that the power of a story comes from what is left unsaid, from the depth and complexity that lies beneath the surface of the prose, like the hidden bulk of an iceberg beneath the waterline. And this metaphor has been widely adopted and discussed in literary criticism and creative writing instruction. Icebergs appear in adventure and disaster narratives, from accounts of polar explorations to fictional stories of shipwrecks and survival, and these narratives often use icebergs as symbols of nature's indifference or hostility, as obstacles to human ambitions, as tests of courage and ingenuity, or as reminders of human vulnerability in the face of natural forces beyond our control. In poetry, icebergs have been subjects of numerous works, with poets drawn to their visual qualities, their metaphorical possibilities, and their connections to themes of time, memory, and change. And iceberg poems often explore paradoxes, the simultaneity of permanence and transience, visibility and hiddenness, beauty and danger, and the tension between the desire to comprehend and the recognition that icebergs, like much of nature, ultimately exceed human understanding. Contemporary art has engaged with icebergs in conceptual and environmental contexts, with artists creating works that comment on climate change, on human impacts on polar regions, on the aesthetics of ice, and on the relationships between art, science, and nature. Some artists have brought fragments of ice into gallery spaces, allowing them to melt as part of the artwork, creating temporal pieces that exist only as long as the ice lasts, commenting on impermanence and on the fragility of frozen environments. Others have created photographic or video installations using images of ice and icebergs, sometimes combining them with sound, with scientific data, or with text, creating immersive experiences that convey the scale and beauty and vulnerability of ice. Performance artists have created works in polar regions, using ice and icebergs as settings and participants in performances that are documented through photography and video. And these works often explore themes of human presence in and impact on remote environments, of the body's experience of extreme cold, and of the traces and marks that human activity leaves on the landscape. In all these varied artistic engagements, icebergs function both as themselves, as physical realities with specific properties and histories, and as symbols, as carriers of meanings that extend beyond the physical facts of ice and water and temperature. And this dual nature, this capacity to be both concrete and metaphorical, is part of what makes icebergs such rich subjects for creative exploration. Whispers of the ancient cold. As we drift deeper into the story of icebergs, let us now contemplate the truly ancient ice that has been frozen for not just thousands, but millions of years. Ice that contains within it information about Earth's past that extends far beyond the reach of human history or even of human evolution. Ice that speaks to us of ages when the world was profoundly different. The oldest ice currently known to science comes not from icebergs, but from deep ice cores drilled in Antarctica, with the oldest continuous ice core record reaching back about 800,000 years. But there is likely ice that is even older, ice at the base of the thickest parts of the Antarctic ice sheet that could be over 1 million years old or more. Ice that has remained frozen through multiple ice ages and warm periods. Through changes in Earth's orbit and axis that have driven cycles of glaciation and deglaciation. Through rises and falls in atmospheric carbon dioxide and methane. Through the evolution and extinction of species. Through the entire span of human prehistory and the emergence of modern humans. This ancient ice is not well mixed, but is stratified, with each layer recording a moment in time, and the deeper you go, the older the ice becomes, and at great depths, the ice has been compressed and deformed by the immense weight above it, so that the layers are no longer horizontal, but are folded and thinned, making the oldest ice difficult to interpret, but still preserving information that can be extracted with careful analysis. When icebergs carve from glaciers that reach deep into ice sheets, they can potentially contain some of this ancient ice, carrying it away from Antarctica or Greenland and releasing it into the ocean as they melt. And while most icebergs come from ice that is much younger, from ice near the surface or edges of ice sheets, where the ice is typically hundreds to thousands of years old rather than millions, there is a possibility that some icebergs contain truly ancient ice from deeper in the system. And identifying and sampling such icebergs would be scientifically valuable, though also technically challenging. The information contained in ancient ice is precious because it provides our only direct measurements of past atmospheric composition and our best proxy records of past temperature, allowing us to reconstruct Earth's climate history with a detail and accuracy that is not possible from other sources, and extending the ice core record to even older ice, to ice that formed during earlier periods of Earth history, is a major goal of ice core science. For it would allow us to study climate during periods that were warmer or colder than anything in the current record, to see how the climate system responded to different configurations of continents, different levels of solar radiation, different atmospheric compositions, and to use this information to better understand and predict future climate changes. The ancient ice also potentially contains ancient life, microorganisms that were frozen into the ice millions of years ago and that have remained in suspended animation ever since. And there have been reports of scientists successfully reviving microbes from ice that is hundreds of thousands of years old. And while these reports are controversial and require careful verification to rule out contamination, they raise fascinating possibilities about the longevity of life in frozen states and about what we might learn from studying ancient microorganisms, how they differ from modern forms, what they tell us about microbial evolution, and whether they possess any novel biochemistry or genetics that could have applications in biotechnology or medicine. The prospect of finding ancient life in ice has also inspired astrobiological speculation. For if microbes can survive frozen for millions of years in Earth ice, then similar preservation might occur in ice on other worlds, and missions to sample ice from Mars or from icy moons might discover preserved life from earlier periods when those worlds were more hospitable. And the study of ancient Earth, ice thus informs our strategies for searching for life elsewhere in the solar system. The philosophy of ice. As we drift toward the conclusion of our journey, let us turn to more abstract and philosophical reflections on what icebergs and ice more generally mean, what they reveal about nature and about our human place within nature, and what contemplating ice can teach us about impermanence, time, beauty, and existence. Ice is a state of water that has been cooled below its freezing point and has transitioned from liquid to solid. And this transition is reversible. Ice melts when warmed and water freezes when cooled. And this reversibility, this ability to move between states, gives ice a kind of impermanence even while it exists. For ice is always potentially water and water is always potentially ice, and which state exists at any given time and place depends on conditions. On temperature and pressure, on the availability of nucleation sites, on the presence of dissolved salts or other substances that affect freezing point, and this conditional existence, this dependence on circumstances, reflects a broader truth about nature, that most of the structures and patterns we observe are temporary arrangements, stable under certain conditions, but subject to transformation when conditions change. Icebergs exemplify this impermanence vividly, for they are substantial objects, containing millions or billions of tons of material, visible for kilometers, capable of damaging or destroying ships, affecting ocean circulation, providing habitat for life, and yet they are doomed from the moment they carve, slowly melting back into the ocean from which they came, existing as distinct entities for a finite period before dissolving, and this finite existence gives them a poignancy, a beauty that is enhanced by the knowledge that they will not last, that each iceberg is unique and temporary, never to be exactly repeated. Icebergs also invite reflection on hiddenness and revelation, on the relationship between what is visible and what is concealed. For the famous fact that most of an iceberg is underwater, invisible to casual observation, reminds us that appearances can be deceiving, that surface observations may miss the greater part of reality, and that understanding requires looking deeper beneath the obvious. And this lesson applies not just to icebergs, but to countless other situations where superficial appearances do not reveal underlying complexities, where what is easily seen or known represents only a small fraction of what exists, and where depth and nuance and hidden connections must be sought through careful investigation and through willingness to question surface impressions. The beauty of icebergs, their aesthetic appeal, also raises philosophical questions about beauty itself, about why we find certain forms and colors and arrangements pleasing, about whether beauty is a subjective human response or whether it reflects some objective properties of the objects themselves, and about the relationship between beauty and meaning. For icebergs are beautiful without having been designed to be beautiful, without serving any aesthetic purpose. They simply are what they are. Shaped by physical processes, and yet we find them beautiful, and this suggests that beauty may arise from certain formal qualities, from symmetry or contrast or complexity or harmony or scale or rarity, qualities that icebergs often possess. Contemplating icebergs also raises questions about scale and perspective. For icebergs exist at scales that exceed ordinary human experience. They are large enough that we cannot take them in all at once, cannot hold them in our visual field or comprehend their full extent from any single vantage point. And this quality of exceeding human scale, of being literally awesome in the sense of inspiring awe, connects icebergs to other natural phenomena that dwarf us, mountains, canyons. Storms, the ocean itself, the sky, and encountering such phenomena can provoke reflections on our own smallness, on the brevity of human life compared to geological and cosmological timescales, on the power of natural forces compared to human power, and these reflections can be humbling, but can also be liberating. For recognizing our smallness and temporariness can help us let go of anxieties and preoccupations that seem large from our limited perspective, but that are actually quite small in the grand scheme, and can help us appreciate the moments of beauty and wonder that we are fortunate enough to experience during our brief time in the world. Drifting into deep rest. As we approach the end of our journey through the mysteries of icebergs, it is time to begin releasing our grip on the details, allowing the specific facts and concepts to soften and dissolve like ice melting into water, leaving behind a general sense of wonder and appreciation, a feeling of having traveled through a realm that is both familiar and alien, both beautiful and dangerous, both scientifically explicable and ultimately mysterious. You have drifted with me through cold waters and through vast expanses of time, learning about how icebergs form and how they move, about their hidden depths and their visible beauty, about their colors and their sounds, about the life they support and the information they carry, about their role in climate and in human history, about the ways they are monitored and studied, about their representation in art and their meaning in culture. And through it all, you have been resting, settling deeper into comfort with each concept, each metaphor, each quiet description. And now it is time to release even the remaining awareness of these topics, to let them fade into the background of consciousness, becoming part of your store of knowledge, but no longer occupying the foreground of your attention. You can imagine yourself as a piece of ice, a small crystal in a vast iceberg, drifting through dark, cold water, slowly dissolving, the boundaries between yourself and the water around you becoming less distinct, the separation between ice and ocean gradually disappearing as you melt, returning to the substance from which you were temporarily differentiated. And this dissolution is not frightening but peaceful, a letting go, a release from the need to maintain separation, to maintain structure. And as you dissolve, you spread out, diffusing through the water, becoming part of the ocean, joining the vast cycling of water that connects clouds and rain and rivers and glaciers and icebergs and ocean in an endless dance of transformation, water changing form but never being destroyed, always present, always moving. And you are part of this dance, you have always been part of it, and you will always be part of it. And right now, in this moment, you are melting into sleep. Dissolving into rest, your thoughts becoming more diffuse, your body becoming heavier and more relaxed, your breathing becoming slower and deeper, and there is nowhere you need to go, nothing you need to do, just this gentle melting, this peaceful transition from waking to sleeping, from consciousness to dreams, or to dreamless deep rest. The icebergs continue their silent journeys through polar waters, drifting with currents, slowly melting, occasionally carving smaller pieces, eventually disappearing entirely back into the ocean. Their journeys complete, their structures return to the water from which they temporarily emerged, and you too are on a journey, the journey of this day ending and night beginning, the journey from activity to rest, from light to darkness, and just as icebergs follow their paths without effort, carried by forces larger than themselves, you too can let go of effort, can allow yourself to be carried into sleep by the natural processes of your body and mind, trusting that rest will come, that morning will return, that the cycle will continue. And for now, right now, there is only the peace of letting go, the quiet of nighttime, the comfort of a safe place to rest, and the gentle dissolution of consciousness into sleep, deeper and deeper, like sinking into cold, dark water, sinking into rest. Into peace, into the quiet that lies beneath all sound, into the darkness that holds all dreams, into sleep, complete and total and renewing, sleep that restores and heals, sleep that allows tomorrow to come, but tomorrow is not now. Now is only this, only the gentle drift into sleep, only the melting away of thought, only the release of the day and the embrace of night. And you are safe, you are comfortable, you are drifting, floating, melting, dissolving, sleeping, deeply sleeping. Peacefully sleeping, and all is well, all is as it should be. And you rest now completely, finally, drifting away like a silent wanderer on a dark sea, drifting into the mystery of sleep, into the ancient cold of dreams, into the depths where consciousness dissolves and rest reigns, and there you will remain until morning calls you back. But for now, for hours, you sleep, and the world continues its slow turning, and the icebergs continue their silent drifting, and all is stillness. All is peace, all is rest.